So, thank you. My name is Pramod Kumar Singh, and I'm from Alliance for an Energy Efficient Economy. And on behalf of the Ozone Cell Ministry of Environment, Forest and Climate Change and the Alliance for Energy Efficient Economy, it is my pleasure to welcome you everyone to this virtual workshop on sustainable cooling technologies in data center. This workshop is an integral part of a joint study that the Ministry and AEEE we are conducting together on promoting sustainable cooling technologies in data center. The study aims to strengthen the evidence base and support India's transition towards energy efficient and climate aligned digital infrastructure. As we all know, data centers today are the backbone of country's digital economy. They enable a wide range of public and private digital services, which are now essential to modern economies. Globally, data centers account for an estimated, and this share is rising rapidly with the expansion of artificial intelligence and high performance computing. To put this data in perspective, if the global data center ecosystem were a country, then electricity demand would be comparable to that of to that of Japan or Germany, depending on the scenario. In India also, this sector is increasingly rapidly. In 2026, the estimated installed IT capacity of data centers exceeded 2.5 gigawatt. Just a year before, the projections were that the data center capacity will reach 8 gigawatt by 2030. But now we are looking at recent trends of the commitments that are being made, and the chances are by 2030, the data center capacity will double the estimates. It's going to exceed 15 gigawatt. With this increasing capacity, there will be a pressure on the electricity system. And as we know, cooling will emerge as one of the most critical end usage that will determine the energy performance and environmental impact of data centers. When we talk about cooling or when we talk about any business, most of you would know that no, we are not projecting these slides yet. This is just the setting the background for the meeting. Cooling is like an overhead. In order to meet the main functions related to computing, cooling acts as a supporting system. So any expenditure, any electricity that goes towards maintaining the cooling is an overhead for the data center. And the lower the overhead, the more efficient a data center is. In today's conditions, most of the data centers operate at an overhead of almost 20 to 30%. And this trend is changing because of the emergence of new data centers technology and enhancements in cooling efficiency. At the same time, data centers and the cooling technologies also rely heavily on refrigerants, which have a very high global warming potential. So the transition in this sector is not only important from a power consumption, energy efficiency standpoint, it is also important from a climate mitigation and refrigerant transition standpoint. Through this joint study that the MOEFCC and AEEE conducting, we are going to examine what are the current IT technologies, what's the trend in the data center growth, what kind of cooling technologies are in place, how the data centers today are operating, what is the operational performance of these data centers. That also will capture. And we are going to look at the international trends, international best practices, which India can look at and adapt as per its own climatic scenario, as per its own development scenario. As part of the project, we are also going to capture some interesting case studies that will inform the future recommendations related to policies and related to what the industries can adopt. In today's workshop, we have a lot of speakers. They represent private sector, they represent government, they represent some of the service providers which are doing the performance measurements and energy audits of data centers. So we are going to look at all of their experience today. And in the course of doing this study and the project, all of you who have attended today will act as a valuable stakeholders who can provide their inputs and participate in this important exercise for India. Some housekeeping rules. Those who have attended the workshop, today the participants are requested to put their comments and questions in the chat mode. The moderators are going to direct it to the appropriate speakers towards the end of the workshop. So we have some presentations today, and we'll take the question and answers towards the end. For speakers, we'll request at the time of presentation, please open their video so that the participants can look at them. It's also requested, if you want to present your own screen, feel free to do that. Otherwise, please request the AEEE team in case you need any help to project your presentation. So with this, I welcome all of you once again, and I wish everyone a very productive workshop. I'll move on to inviting Santosh. Do we have Mr. Aditya Narayan Singh ji? So hello, sir. Good afternoon and welcome to the workshop. And we request you, sir, for your keynote address. Thank you, and over to you.
Thank you very much. I am audible?
Yes, sir, you are.
Good afternoon to all, and I welcome you all to this National Stakeholder Consultation Workshop on the study on promoting sustainable cooling in data centers in India, which has been awarded to Alliance for an Energy Efficient Economy by the Ozone Cell MOEFCC under Stage 3 of the SCFC Phase-Out Management Plan under the Montreal Protocol. Since many refrigerants are either ozone-depleting substances or HFCs, their production and consumption are regulated under the Montreal Protocol framework, with the ozone-depleting substance controlled under the original treaty and HFCs controlled through the Kigali Amendment. So just I want to give you background. The Montreal Protocol is one of the most successful multilateral environmental agreement, and the protocol regulates the production and consumption of ozone-depleting substances and also addresses a phase down of HFCs under the Kigali Amendment adopted in 2016. Since joining the Montreal Protocol, India has consistently demonstrated its commitment to phasing out ozone-depleting substance. India successfully eliminated the use of CFCs by 1st January 2010, carbon tetrachloride and halon by 1st January 2010, and methyl bromide and methyl chloroform for control uses by 2010, and HFC, SCFC 141B by 2022. And today, India continues its transition under the accelerated hydrochlorofluorocarbon phase-out management plan, that is known as HPMP, currently in a stage 3 in line with the global target of completely phasing out SCFC by 2030. SCFC phase-out is being implemented through technology conversion to non-ODS and low GWB alternatives, along with training, capacity building, and awareness generation in India. SCFC has been phased out in manufacturing of new equipment as of 1st January 2025. while activity in RAC servicing sector will continue until 2040. India is also implementing its commitment under the Kigali Amendment for phasing down of HFCs and promoting adoption of environmentally sustainable and energy efficient cooling technologies. India also launched the India Cooling Action Plan in 2019, which focuses on reducing cooling demand, refrigerant demand, and improving energy efficiency and promoting better technology options. India's data center sector is one of the fastest growing digital infrastructure sector, and data centers are highly energy intensive facility, and cooling system account for nearly 30 to 50% of total facility energy consumption. Cooling infrastructure in data center rely on refrigerants, which generally has a high global warming potential. So as the cooling demand continues to grow, the data center has an important role in the refrigerant transition through the adoption of sustainable cooling technologies and low GWP refrigerants. In this regard, Ozone Cell MOFCC has launched the study on promoting sustainable cooling in data center in India under the HPMP Stage 3 to understand about the current cooling technologies, refrigerant requirement, energy use, and operational practice in data center, while assessing global development in low GWP and non-ozone depleting substance cooling solution. And it will review standard regulation and implementation experience to identify practical opportunities for improving energy efficiency and cooling performance. Based on findings, the study will develop actionable recommendation and best practices to support the adoption of efficient, reliable, and future-ready cooling system in data centers. And we also look forward to valuable feedback, technical inputs, and recommendations from all the stakeholders present here today. The consultations and discussions from this workshop will contribute towards strengthening the study and supporting evidence-based recommendation for sustainable cooling practice in India, rapidly growing data center sector. I encourage all participants to actively engage in today's discussion and share their perspective and experience. Now I request AEEE to start the discussion. Thank you.
Thank you, sir, for your opening remarks and also highlighting the importance of data centers as part of India's commitment towards climate change and adoption of environment-friendly technologies. So next in the segment, we have 5 presentations, and I see comments from the audience who were requesting to share the screen. There was no presentation made until now. Now we'll start with a sequence of presentation. First, I will invite my colleague, Dr. Santosh Sani, for giving a context-setting presentation. Thank you, Santosh, and please share your presentation.
Sure. So I am sharing my screen and PPT. Hope my screen is visible to all. So in this presentation, I will be sharing about the introduction and background of the data centers. What is the growth rate in India and globally? Type of data centers and cooling requirements, and energy consumption patterns in various data centers. Why the refrigerant transition imperative is there, and how we can achieve the sustainability in data centers through various means. I'll also share the study objectives, what we are looking for. So data centers are like typical facilities which store, process, and distribute data, and are considered as a backbone of the recent high performance computing, AI, telecommunication, etc. Data centers are mainly have like almost 6 type of components, in which IT infrastructure is the one, which have servers, rack, blades, GPUs, etc., which do the main function of the data centers. And we have auxiliary components, to support the IT infrastructure like cooling systems, electrical and power monitoring, etc. And they have various subcomponents to support that operation of the data centers. This is the global view. Like United States leads the data centers in numbers, in total installed IT capacities, power consumption, etc. Globally, we have around like 10 terawatt hour of electricity consumption from India, and that is about 0.8% of total grid electricity consumption. And you can see in the world global map that India's data center in terms of numbers is very small, and also is in the capacity wise as well. If we see into the third graph, where we can see in India, number wise, there are about 300 data centers located at various locations. Mainly, a few cities like Mumbai, Hyderabad, Chennai, Bangalore are the leading hubs of the data centers. Uh, which has the maximum number of data centers, and now it is shifting towards the tier 2 cities as well, and a few cities like Visakhapatnam, Vizag in Maharashtra, Raigad, etc. are emerging as the new hubs for the data centers. In this slide, you can see that data centers in India in 2022, the installed IT capacity was around 375 megawatts, and in 2025 it becomes 1500 megawatt, and by the end of 26 we will with the same growth rate, if we go, it will be about 3000 megawatts or 2900 megawatts. In the recent industry reports, and if we see last 5-6 months industry reports, the projected capacity is in the range of 8 to 10 gigawatt IT load of the data centers. But if we consider the recent announcement by various stalwarts in the data center industry, a few announcements you might have seen, and here in the screenshot I have mentioned them, that Reliance is planning to go with the data center. Recently, Adani also committed. AirTrunk announced 5 gigawatt of digital infrastructure data center capacity building in India. So the total investment is about $200 billion, and which will the growth is like by 2030, 2032, it will be about 17 gigawatt IT capacity. So this is the like huge growth in terms of capacity, in terms of numbers, because most of these facilities are hyperscalers in nature. So the numbers will be about 320, 325 gigawatt numbers, but the capacity will be huge. In terms of type of data center, so mainly there are three types of data centers, mainly dominated: enterprise, co-locations, and edge data centers to applicable for various telecommunication and day-to-day requirements of data center. But now hyperscaler data centers are increasing, and here in this graph we can see that energy consumption distribution in typical data centers. So in enterprises, we can see that the cooling part is about 30 to 40% of total data center energy consumption, whereas the co-location is in the range of 25-30%. But if we look at this hyperscalers, so hyperscalers, the percentage of cooling is very low, in the range of 10 to 15% only, and the servers energy consumption is very high. That means that the core energy consumption by cooling is low, but the overall energy consumption by hyperscalers will be very high in quantum. So the efficiency, energy efficiency in cooling systems is improving. The temperature requirements in data centers is a bit different. Cooling strategies will change, and that's why like the main energy demand will be from the IT infrastructure, and the cooling will be having a lesser. So in the hyperscalers, was the like reason that the energy demand is increasing, and why the cooling intensity or the importance of cooling is improving. So we can see in the graph that in hyperscalers, mainly to support the AI and compute, and that high performance computing, big data and analytics, we need GPUs. And in last 1 decade, the GPU's thermal design power has increased about 6 times. So recently, the various announcements are there which will have one GPU will be having about 1800 watts per chip. And that electricity or that will be directly converted to the heat. So basically, the heat flux of the servers or the chips is increasing, and that's why the more precise, more to the point cooling is required because of this increasing heat flux. This is an energy consumption distribution of typical data centers of colocation in type. So we can see that cooling is consuming about like 38%, in which that is like cabinet cooling and air conditioning is part. But now, because of the high densities, it is shifting towards the liquid cooling. So it will again change with the time, and the other electricity consumption components are also highlighted here. In India, it becomes more important because India's climatic conditions are a bit different than the cold climatic conditions. Tropical climatic conditions have high temperature and humidity, and that's why the cooling energy consumption will be a bit higher compared to the other counterparts. Also, the shifting in the overall rake power density is increasing. Earlier, it is in the range of the average power density was about like 8 kilowatt per rake, but now it is shifting towards 100 plus kilowatts per rake, and that's why the cooling importance will increase. As mentioned by director, the refrigerant transition. So we will be implementing the Kigali Amendment to the Montreal Protocol, and we have to shift towards the other alternatives of refrigerants. Currently, we are almost using like HFCs and a few HFOs, which are having very high ZWP HFCs and a few HFOs. But now, because the phase down of the HFCs, we have to shift and identify other alternatives, which might be HFOs or maybe natural refrigerants. And all these refrigerants come with some cost, they are flammable a bit. Flammable in nature. Efficiency, we have to take the trade-off, like what will be the efficiency of using various, how the thermophysical properties of various refrigerants will change the optimization and which refrigerants to be used. So these part will be covered in the study as well. To have sustainability into the data center, so there are a few pillars which can be explored while exploring the sustainability. And one of them is the cooling technology, like how we cool the data centers or the servers. What are the refrigerants we use? We can go with the low GWP refrigerants and refrigerants which have higher efficiency while working with the cooling systems. We can have waste heat recovery, wastewater recovery, etc. And again, renewable energy integration in the data centers will again add the sustainability parameter. To support the recent growth in the data centers, a few states have come out with data center dedicated policies, which includes various things like infrastructure support, green incentives, tax benefits, renewable energy integration, etc. And the states are regularly exploring how the sustainability angle can be explored as well, because all these support the data center growth rate, but also the sustainability angle has been started in, considering in various state policies. So a few states where the data center numbers are or the capacity is high, they have come out with a few policies, and again other states are also considering coming with dedicated policies to support the data center growth and sustainability. In this slide, I am seeing the study objective. So, what the study Director Ozone sir and Pramod sir have mentioned. So, in this study, we will be doing the review of cooling technologies. What are the refrigerants we can have in the data centers? How the energy use pattern is changing with adoption of these measures. We will also explore the O&M practices, the cooling, again, assessment of airflow management, maintenance, leak detection, and how we handle the refrigerants throughout the life cycle. We will explore the operational challenges, how the efficiency can be improved, assessment of emerging alternatives of refrigerants, and a review of the national, international cooling and refrigerant demands. And we will be coming with the stakeholder consultations. We will be doing a number of consultations. So 2 will be virtual workshops, and out of that we will be framing the recommendations by the various stakeholders in the industry and will be included in the study. So that's all from my side. Thank you. And over to you, Klaus.
Yeah, thank you, Santosh, for the context-setting presentation. Now we'll go into the 4 thematic presentations. We'll start with Ms. Jennifer Chang, who is Associate Vice President at AirTrunk. AirTrunk is also a member of Asia Pacific Data Center Association. Thank you, Jennifer, for joining us today. And over to you for your presentation on regional best practices and approaches towards cooling data center in a sustainable manner. Over to you, Jennifer.
Thank you. Are you able to hear me?
Yes, you are audible.
Excellent. Great. Thank you, AEE, for inviting AirTrunk to join this discussion. I believe you can see my screen. Great.
Yeah.
So I'm Jennifer Zheng, AVP of Sustainability at AirTrunk. AirTrunk is also a founding member of the APDCA, which is the Asia Pacific Data Center Association, which brings together leading data center operators to share practical experience and support the sustainable growth of digital infrastructure across the region. So just to give you a bit of background, at AirTrunk, we developed and operate hyperscale data center across Asia Pacific, the Middle East, and India. So my perspective today is from an operator lens on how sustainability considerations show up in real decision, operational, and investment decision. And cooling is one of the most important sustainability topics for data centers. It can account for a significant share of facility energy use. And as digital infrastructure grows, particularly with AI and higher density workloads, the way we cool data center will become even more important. But I want to start with a simple point. Sustainable cooling is not about choosing one best technology. It's about making the right decision for the right location with a clear view of the trade-off. And that is especially relevant for a market like India. India data center sector is growing quickly, as mentioned earlier, but it's also a market with high temperatures, different level of water stress across regions, grid constraints in some location, and an ongoing transition towards low GWP refrigerant. So the question today is not simply, should we use air cooling, water-based cooling, hybrid cooling, or liquid cooling? The better question that we should be asking is, what cooling approach delivers the best overall sustainability outcome for a specific site, in a specific climate, with a specific workload and resource context? And that's the framing that I want to share today. So when we talk about sustainable cooling, there is often a natural question. What is the best cooling solution? But in practice, there's no universal answer. The most sustainable approach requires balancing multiple factors at the same time, as you can see on the slide. Energy efficiency is, of course, critical. Cooling decisions directly affect how much electricity a data center requires. And in markets where grids are still decarbonizing, every unit of energy saved matters. But energy is only one part of the equation. Water is also very critical. A water-based cooling solution may improve energy efficiency, but in a water-stressed location, that may not be the best or most responsible outcome. And this is particularly relevant in part of India, where water availability, water stress can vary significantly by region. The next point will be reliability and resilience also cannot be compromised. Data centers support critical digital infrastructure, so cooling systems need to perform under high temperature, changing climate conditions, and strict customer availability requirements. We also need to consider the broader climate impact, like refrigerants, embodied carbon, equipment replacement cycle, and how quickly lower impact technology can be adopted without creating unintended consequence. And finally, we need to consider customer workload requirements. Higher density AI workload may require different cooling strategies from traditional enterprise or cloud workloads. So the key message is that sustainable cooling is not about finding one perfect technology. It's about making informed, context-specific decisions that balance energy, water, resilience, together. And that brings me to the first principle, climate responsive design. So across Asia Pacific, we operate in different environments, and each market will have different temperatures, humidity levels, water availability, grid characteristics, and regulatory expectation. And these local factors have a significant influence on what cooling solution the most sense. So for example, water-based cooling can provide energy efficiency benefits because water is an effective medium for heat rejection. However, this does not mean that water-based cooling is always the most sustainable choice. In regions with high water stress, we need to carefully evaluate the impact on local resources and whether dry or hybrid solution may be more appropriate. And this is why we look beyond individual metrics. And we all know that historically, the data center industry has focused a lot on PUE, and we know PUE remains extremely important, but a lower PUE alone does not tell the full story. We also need to consider water efficiency, carbon impact, and local resource constraints. And at AirTrunk, water stress and availability are assessed early on during site selection and design. And where water-based solutions are appropriate, we also explore opportunity to reduce reliance on potable water. So that includes collaboration with utilities on recycled water solution. Ultimately, the most sustainable cooling system is not necessarily the one that uses the least energy or the least water. It is the one that that is best optimized for the environment where it operates. The second principle is that efficiency does not end once the data center is built. Design creates the foundation for operation that determines whether that efficiency is sustained over many years. So a data center is a long life asset, and performance needs to be continuously monitored and optimized. For example, at AirTrunk, we monitor operational performance, including tracking PUE trends, and we constantly identify opportunity for improvement. We also know that preventive maintenance is also important. We ensure equipment continue to perform as intended. And another important element is knowledge sharing. Operating across multiple campuses across Asia Pacific allow us to have lessons learned from one location to be applied across the portfolio. And we also look at innovation opportunities. For example, water optimization initiatives, such as recovery system that can help improve operational water efficiency where sustainable. So sustainable cooling is not just a design decision made at the very beginning, but it also requires ongoing optimization throughout the life cycle. And as sustainability expectations evolve, the industry also needs to think beyond a single metrics. So improving energy efficiency remains fundamental, yes, but the overall climate impact of cooling involves multiple dimensions. So let me take you through. So from a scope 1 perspective, this includes direct emissions such as refrigerant, and refrigerant transition is an important topic for the industry, particularly as lower GWP alternatives become more available. However, this transition also needs to be managed thoughtfully. Replacing the equipment too early may reduce refrigerant impact, but it could also create additional embodied carbon impact. For scope 2 perspective, improving operational efficiency helps reduce electricity consumption alongside the transition towards renewable. And from a scope 3 perspective, we need to consider the materials, the equipment, the life cycle impact of the infrastructure. So the future of sustainability is moving from optimizing individual indicator to understanding whole life cycle impact. And the goal here is not to improve one metric while shifting the impact somewhere else. It is to optimize the overall environmental outcome. And looking ahead, cooling will continue to evolve rapidly, particularly with the growth of AI and higher density workloads, as I mentioned. And this changed the conversation. The question is no longer, how do we cool efficiently today? It is also, how do we redesign infrastructure that can adapt for the future? We expect the future will include a combination of solutions like liquid cooling readiness, hybrid cooling approaches, smarter control, and greater use of data and analytics. And different workloads may require different approaches, and flexibility will be increasingly important. The next generation of sustainable data centers will not be defined by one cooling technology, but by smarter decision-making frameworks. And finally, sustainable cooling cannot be solved by one organization alone. It requires collaboration across the ecosystem. And this is where APDCA can play an important role. By bringing operators across the region, it provides a platform to share practical experience, identify common challenge from the ground, and support more informed dialogue with government and the industry. And this is particularly valuable across Asia Pacific, where markets vary significantly in climate, infrastructure maturity, resource availability. And each one play a role, like operators. We have a role to play in efficient design, operational optimization, and transparent performance measurement. Customers are also critical because IT hardware choices, workload characteristics, and operating requirements directly influence cooling strategy. Suppliers are also essential partners in helping us to develop the next generation technologies, lower impact equipment, and lower GWP refrigerant. And finally, policies and industry organization. They also have an important role in developing frameworks that encourage sustainable outcome while recognizing regional differences. If there is really one message today that I would like everyone to remember, it is that sustainable cooling is about balance. It's the right technology in the right location, supported by the right partnership. Thank you.
Great. Thank you so much, Jennifer, for that very insightful presentation. We'll request if you can stay till the end, because I'm sure participants will have a lot of questions and they would like to understand from your experience. We are also glad to note that organizations like Asia Pacific Data Center Association, how it's becoming a platform for many stakeholders to connect, learn, share, and grow. And that is something which, again, is very sort of inspiring. Moving on with our, today's agenda. Next, I will invite Dr. Jubin Varghese, who is a Senior Director Innovation at Trane Technologies. Most of us are aware that Trane is among. Yes, Jubin, we can hear you. And my request is if you can turn on your video as well, so that all participants can see you. Over to you,
Good afternoon.
Jubin.
Yeah, good afternoon. Can you hear me?
Yes, we can hear you. Jubin.
Yeah, I wanted to talk today when this subject came about sustainability in data centers. One of the big unmet or in a low-hanging fruit, which I think is there, is the waste heat. When we talk about a 1 gigawatt data center, you are talking about around 1.25 gigawatts of waste heat, because all this heat has to be dissipated and it goes out to the sky or to the environment and causing, enormous damage. So how can we use this waste heat, not only to reduce the environmental effects, but also use it to cool, or how to use that energy, because this is heat is energy, and and how to use it was the key question. So one of the things we must realize when we look at waste heat from data centers is, especially from when you have the HVAC equipment, it is a low grade waste heat. So it is very difficult to use low grade waste heat that is around I would say 35, 36 degrees. But with this new chips which are coming up, Vera Rubin and other things from NVIDIA, the waste heat, the temperature can go up to 47 degrees centigrade. So this, people have started to use this waste heat for many applications. Some of the applications where Trane Technologies is really looking is, one is using this waste heat for additional cooling, and this is using absorption chillers. That is one way. The second way we are looking at using this waste heat is to produce atmospheric water generation. That means you produce water from the atmosphere using the waste heat. This is also an absorption process where, when air is passed through a material, it absorbs the water, and then we use the waste heat to get that water. So I am just giving these two examples. Then we are also using it quite a bit at the present time in district heating. That is already there. But these two things I wanted to say, that we can use reclaim. You can get additional cooling, and also we can get additional water using waste heat. So this happens when there is low grade waste heat. But when at present time, a lot of these large data centers, they also have on-site power generation. When you have on-site power generation, you have got really high grade waste heat, and that we can use it again for these kind of things, like even it can be used also to produce more power, like cogeneration, or using it for organic Rankine cycle and things like that. So my main message today I wanted to really convey is that there is a lot of heat available, which is energy in these data centers, and this can be easily utilized to increase not only the power usage efficiency, but also the water usage efficiency. And this can our calculations and our blueprint shows that we can at least we can increase the efficiency of the PUE from 1.25 to 1.05 and things like that, which is a large number of tokens. So this was the message I really wanted to convey, that the waste heat is a very important aspect we need to look into when we want to look at sustainability. Santosh, can you hear me? Oh,
Yes. Hello. Yes, we can hear you, Zubin.
Yeah. So that was the message I wanted to give. The slide which you have, the first slide, if you look, You can see that's the actual Google data center, and you can see the amount of steam or heat which is going, going away and as waste. So we can use this waste heat to basically, increase the PUE and WE. Another problem with this waste heat, what we are doing today is, it goes outside into the surroundings, and it really affects the, climate around. It is known that all this waste heat can really increase the temperature surrounding by up to 4 to 5 degrees. It may be more, but we have modeled that, we have seen that it can go up to 4 to 5 degrees. So it is very, very important that we, utilize this waste heat for something useful. Thank you.
Well, thank you so much, Jubin, for bringing this perspective that, designing efficient manner alone not sufficient. We have to also look at all possible ways to improve the efficiency, whether it's utilization of waste heat. Um, um, that is also very important for cooling or for any other productive usage. And we heard from you as well as from the previous speaker, Jennifer, about the importance of water usage efficiency. So that is also something which is going to be very important for India. So thank you so much for your presentation. I will now move to another related topic, which is going to be optimizing the cooling system in data centers. Again, what we heard from Jubin as well, that it's only design is not important. We have to also ensure that data centers perform at the right level of efficiency. So performance matters. So our next speaker is Mr. Upendra Pratap Singh. He's a director at Sust Energy Solutions. He has been doing energy audits, resource efficiency audits of various data centers across India. And we hope that in his presentation, he will bring some of that practical aspects of how data centers are performing and which are the areas of improvement. So with this, I invite Mr. Upendra Singh ji. The floor is yours.
Okay, thank you, Pramod ji. So I'll just share my screen. Just allow me 1 minute.
And Upendra ji, as you are projecting your screen, we can hear you very well. If you wish, you can turn on your camera also.
Yeah, just hold.
And I'm also requesting participants to keep pouring your questions and comments. And speakers who wish to respond to those comments can use the chat mode, or otherwise we'll take it up in the last Q&A session.
Just, is my screen visible now? Just,
Upendra ji, we can see you, we can hear you, but your slides are not showing up.
just give me 1 minute. My screen is not visible to you?
No,
Hello?
not yet. No, we can't see it. AAA team, do we have a copy of Upendra ji's presentation? Can we project it from our end?
Yes, we can do that. Upendra, so I am presenting slides.
Because I'm not able to share this.
Let me share your slides. Now we can start when I have shared your slides.
Okay. Just a minute.
So Upendraji, we are projecting slides from our end. You can please start the presentation.
But I'm not able to see the slides.
It's projected for all participants.
Okay. So
Okay.
we will start. So good afternoon, everyone, and thank you very much for giving this opportunity to speak about this cooling optimization in data centers. So we have made this agenda. So we will first discuss about the context and sustainability. This is the session roadmap slide, and why cooling matters in what is the trends in India data centers and what is the impact on sustainability. That is one of the areas. Then other slides we will discuss about the field reality, where we will discuss about the loading of the IT power and airflow gaps and overcooling and control gaps, how we can address these issues. And then on some slides we will discuss about the optimization levers, where we can optimize like airflow or temperature resets or use of BMS. And then we'll be discussing about the PUE, what are the probable ECMs, what is the impact on carbon emission reductions. And at the end we'll discuss about the operating pathways, how we can take further. So this is the next slide where we will discuss why cooling optimization matters. So if you see in the data centers, our cooling contributes to around 35 to 40% of the total power consumption. And so there are three levers. One is the energy. So even a small cooling inefficiency becomes very large, because if you save even 1 kilowatt, the data center is operating 24/7. So annual figure is very high. So we need to save each and every possible watt in the cooling. That is important. Then next is the reliability. So it is very important to maintain the uptime of the data centers. So we need to avoid the hot spots, or if there is a bypass of cold air or hot air, that we need to capture, and we need to avoid the recirculations. So that is the other area. And next is once we reduce this consumption, certainly it will translate to the sustainability lever. So lower costing units means reduced emission. So that's why it is very important to optimize the cooling power in the data centers. Then we'll discuss what are the trends in data centers. So one concept is that now we are working on the clouds, AI, and new technologies. So now our rack densities are increasing. Initially, we were operating at 6 to 7, 8, or maximum 10 kilowatt rack density. Now 15 to 20 kilowatt rack density is very common. And with the increase in rack density, our cooling demand is heavily increasing, and we need to optimize the cooling power. The next point is we need a 24/7 reliability of the data centers. Even a small breakdown is not acceptable, because we are doing so many financial transactions and important tasks. So uptime is very important. Up to 99.99% people are guaranteeing, the data center providers. And now most of the operators, they are continuously monitoring their data center PUE, that is power usage effectiveness, what PUE labor they are maintaining. So many data centers are doing a benchmark studies also to know what the other peers are operating, at what efficiency they are operating. So we have done some studies and we found there is a variation of say around 1.4 to up to 2.1. So there's a wide range of the PUE that we need to address why other people are operating at a higher PUE, how we can minimize those. So that is one of the concerns people are working out. And certainly, as we all know, there is a pressure on sustainability we have to become net zero, and then each individual corporate is also being given the target to reduce their carbon emissions. So since cooling is the major energy consumer in the data center, it is very important to optimize our cooling energy to meet the sustainability goals. The next slide is about the Indian data center sustainability context. So cooling optimization links the uptime assurance, because once we optimize our cooling, we also address many critical issues which are linked with the reliability and uptime of the data centers. So how does this matter with the sustainable operations? One is the rising digital load, as we discussed earlier. So now the cloud, AI, and 5G, etc. are coming, and they're demanding for higher cooling loads. And cooling is one of the largest adjustable support loads without touching the IT power, because IT power we cannot touch. Anyway, it has to work as it is working. And next is the grid and peak impact. So once we optimize the cooling load, we can also relieve the grids from the additional loads which is being demanded nowadays. So that is also, it is very important. And of course, the operations must maintain under the high ambient temperatures, dust, humidity, and water constraints. So we need to be climate resilient. So this is also one of the very important topics for optimizing the cooling energy. So the idea is that first we need to reduce the avoidable cooling energy, then we need to protect the rack inlet temperature and redundancy, and then convert the savings into verified carbon reductions. So that is the roadmap we need to follow. So the idea is just not to add some cooling capacity or add additional PSCs, etc. So first we need to optimize the cooling. Then we need to add the capacity when we find some reliability gap. Reliability gap means we need to know how much kilowatt is the IT load, how much is the cooling loads. So then we need to consider what redundancy level we are looking at. And then we can decide that existing cooling capacity is sufficient or not, or should we go for any addition of the units. So we need to understand what are the challenges, key challenges observed in the cooling. So there are 3-4 levers in that. As we discussed, first is the low IT loading. If our IT loading is come, because based on the studies done in data centers, we observed that most of the data centers in India are operating between 25 to 65% loading. And some data centers we found they're even operating at 6-7% loading. They are newly installed data centers, not fully operational. So that's why the loading is very low, but the PUE is very high. In their case, we found a PUE of 2.1, 2.2, up to 2.4 also. So low IT loading is one of the levers which is affecting the efficiency of the cooling. Then second lever is the airflow. Airflow management is also very important in the data centers. So when we do the studies, we find that sometimes the cold air, hot air mixing is there. Or if you see some older data centers, even racks are not arranged properly. So we need to make a proper hot aisle, cold aisle arrangement. Now most people are aware and they are doing it, but still there are some facilities where you will find that there is a mismatch. So hot aisle, cold aisles are not properly designed and there is mixing affairs that we need to address. And when we do the actual measurements and site, we find that at some places there is overcooling, some places there is undercooling. So that also we need to check and maintain, because what happens that mostly the people install one or two sensors in the server room, and then they check the temperature and accordingly switch on, switch off the ACs or PSAs, whatever cooling units are there. So that is not correct the way. Sometimes you need to check the temperature at the rack inlet. What is the actual air temperature going into the racks? So there we will actually come to know whether our temperature settings are perfect or not. So that we need to check periodically and maintain that. Then control is very important because now we are coming with the BMS to sequence the units, maintain the temperatures. So that control logic is also very important, and the sequencing of our units. So which unit needs to be run first, which needs to be second. So first we need to understand the operating efficiencies of those units, and then we can properly design the sequence of operations. So that's how we are going to plan this coming data centers. So lower loading does not automatically mean that there is a lower PV only due to loading. So control tuning and other airflow contaminants also decide how much PV we are going to maintain. So based on the many assessments we did in the various data centers in India, here is the summary we have prepared, that what was the actual outcome. So it was observed that low load was common, but it was not the only issue. So PU sensitivity increased at low load, but airflow discipline and controls separated better sites from poor performers. That was one of the observations. Then we found that the airflow gaps were visible before doing some analytics, because once you enter into data centers and start doing measurements, we come to know there is a gap in the airflow. You can find many cables which are obstructing the path of the airflow. So that we need to take it out, because with the passage of time, people keep putting the cables and they obstruct the path. So the flow of air is get diverted and you don't get the proper air at all the racks. Then control logic, sometimes they always keep conservative. So instead of setting a temperature of 24 or 23, they will always set a temperature of 20 degree, 19 degree, like that. And also sequencing is done by mostly manually. So many sites are there which don't have any proper BMS or control logic to operate the PCs. It is based on the operator judgment. So they can switch on any unit, they can switch off any unit. Sometimes they also switch on the standby units, which has further redundancy. So those things needs to be taken care, and the operators needs to be trained properly. And the fourth observation was optimization potential was mostly operational. So mainly it was related to the operation side. So if you see just so if you see the right hand side graph where recurring cooling performance gaps, so most of the time we see the low IT loading, conservative set points. These are the most commonly found problems. Then bypass leakage, this is also a common problem. Sometimes we find the poor cooling staging, or rack inlet not uniformity, or fixed speed auxiliaries. Yes, some of the sites they don't have control automation to install drives to control their fans, etc. So that is also one problem, and we can take it care by doing better automation these days. So next we will discuss specifically on the airflow management opportunity, how we can do the airflow management. So cooling capacity may be available, but sometimes air bypasses the IT load. Due to uncontrolled leakage paths. So some of the problems which affect the airflow management is one is the oil discipline. So we need to maintain the proper hot oil, cold oil separation so that the hot and cold air don't mix. So we need to maintain the front to front and rear to rear rack alignment and oil mixing. So this is one of the thing, and many people are now installing these containments and maintaining the hot oil, cold oil arrangements. Second very common observation we do in their flow management is blanking panels. So many times we observe that they don't put the blanking panels, and cold air passes through the rack directly and mixes with the hot air. So effectively increasing the temperature. So we need to close all the unused U spaces, especially where the rack density is high, so that we can avoid the hot air recirculation. So this is one of the areas. And third area is the floor and cable openings. So when we see that we need to seal the cable cutouts because the air goes from that area also. Sometimes there are some unused floor tiles, so it should be properly sealed. So it should not be a perforated one, it will be a closed one, so that we can avoid the leakage. And then we have to avoid the rack leakage plus return path. So we have to close the side gaps and keep PSC and crack return path clear to avoid short circuiting of the supply air. So these are some of the steps we can take for a proper airflow management in the data centers. So we have to seal the bypass paths before reducing the set points and adding the cooling capacity. So that is the key takeaway from this. So next slide, we will discuss about how we can optimize the temperature.
Penderji,
Yeah.
Well, Pramod here. So in the interest of time, I'm requesting if you can cover the remaining slides quickly so that we'll have more time for Q&A. Thank you.
Okay. So in the temperature optimization, there are the 4 levers. One is the set point review. So we have to start with the current supply return trends, rack inlet temperature, and see if there is any complaint history. Then we have to maintain the ASHRAE envelope. ASHRAE envelope says that normally it is 18 to 27 degrees centigrade for the class A racks, but for high density racks, now there is a new guideline. So 18 to 22 degrees centigrade temperature we need to maintain. And then we have to avoid the overcooling. So this gives at least 2 to 3 degrees centigrade opportunity for optimizing the cooling. And then we have to do the proper monitoring. You have to do at the rack level, then trends in the BMS. So these parameters are important to optimize the temperature and subsequently reduce the cooling power. Then is the controls, how we can optimize the cooling by the controls. So one is the sequencing of the PSCs. Second is the use of VFD or EC fans wherever feasible. Then we can put sensors and BMS logic. And also we can control our humidity, and if there is a possibility and clean air, we can think of the free cooling. So these are the 4 areas we can work to control the temperature for optimizing the cooling. So this slide just to show what is the impact of reducing our cooling power and the overall PUE. So this is we have shown by example that if a 2 megawatt IT load and our cooling load is around 0.8 megawatt, others loads see 0.3 megawatt, then existing PUE is 1.55. The normally practically possible reduction in the cooling load is 10 to 20% can be achieved. So if you reduce the cooling load by 200 kilowatt, then our PV will come down to 1.45. So this just to be given an example. So there will be other impact on the facility demand reduction, and it will also translate to emission reduction. So based on the various studies done, just we have summarized what are the probable ECMs for improvement and what are the lessons we have learned. So we have found that most of the ECMs are low risk ECMs. The real success factor is a disciplined implementation and verification. That is very important. So basically we have categorized the ECMs which we found in data centers in the 4 categories. One is the airflow management, like installing of blanking panels, cable ceilings, which we discussed earlier. Then control and sequencing. Then review of the set points and improve it if required. Then optimization on plant and fan. So these are the 4 main focus areas where we find the opportunities. And measurement and verification is also very important to ensure that we are sustaining our implementations. So very important thing is that we should not change the all set points together. We have to do some control trials, and we have to involve the O&M team, bypass the controls quickly, erase savings. We have to update the SOPs also for long-term benefit, and sequencing alarms, manuals overrides, and review the frequency. So we need to understand what is the environmental impact by doing the optimization. So from last example itself, we have just calculated if we save the 200 kilowatt, and we will save around 1.75 gigawatt hour per year, and it will translate to around 1,240 tons CO2 per year at the current grid emission factor of 0.71. So this is one of the key messages for sustainability. And so what is the pathway to sustainable and resilient operations? So first step is that we have to create a baseline, do the proper metering where we can monitor our kilowatt, PUE, temperature, runtime. Then we have to fix our airflow. So we can install the blanking, ceiling, oil discipline, etc. Then we have to tune the set points, very stepwise trials within the guidelines. Then we have to automate the controls where we can do the sequencing, alarms, VFD logic, and manual overrides. Then we can verify the savings and unlock it for the long term. So important thing is that the reliability is very important, and we have to start with the low risk corrections and do not trust one day savings. So we need to continuously monitor that to ensure that it is sustainable. So first is reliability, then you have to trend, and then scale by the proven logic. So that is the idea we have to follow. So I think that is this from my side. So we are ready to take any questions. Thank you.
Yeah, thank you so much, Upendraji, for this presentation. And thanks for sharing with us your field experience, the kind of gaps that you have observed, and also presenting the right sequence in which the energy conservation measures need to be adopted. A lot of insights, a lot of action points. At this stage, I would like to mention before all the participants that as part of the project that we are undertaking with MOEFCC, there is an option for us to do a lot of field studies, do the actual energy assessments of data centers. So in case someone wants to participate in the project and make their facility available for study, please reach out to AEEE team. Thank you. And with that, we'll move on to the last presentation for today. And we have Mr. Indrajit Shah, Associate Director, Sustainability and ESG from CBRE. CBRE is one of the world's largest facility management company working on sustainability solutions. And Indrajit is going to talk about the trends of GHG emissions and water usage when it comes to cooling in data centers. So with that, Indrajit, over to you. You have roughly um, um, 12 to 15 minutes to cover your presentation.
Thank you. Am I audible?
Yes, Indrajit, you're audible.
Okay. There is some issue with my video, but what I'll do is I'll share my screen in the interest of time so that we can continue with the presentation. Yeah.
Sounds good.
Is my screen visible? Can you see the presentation?
Yes, Indrajit.
Okay, that's great.
Can you please put it on a full screen mode?
I have.
Thank you.
Yeah. Great. Thank you so much. And thanks everyone for listening in. My name is Indrajit Shaw. I lead the sustainability and ESG business for CBRE India. Today, we'll just talk about quickly on three things. One is the overview of the Indian data center market. Then we will quickly talk about the GHG emissions related to cooling. And finally, the water usage and the impact of that. So quickly, from a data center perspective, it's growing at a 17% CAGR from 25 to 26. As you can see, it's grown from 19.5 to almost 23 billion. And this is an overview from some of our reports that we have produced in terms of what is the largest area in, from a data center perspective. So as you can see, we have got Mumbai, which leads along with Pune, Hyderabad, Bangalore, and Chennai. And some of the other locations include Kolkata, Lucknow, Jaipur, and Patna. So this helps you understand which are the tier 1 markets, tier 2 markets, and within the tier 1 markets, which are the emerging ones and which are the established ones. So this is important to help you understand what are the solutions available in each of these locations and how they can be tailored to the market there. What's driving this expansion? Of course, digitization and internet usage and the rise of AI. What is also interesting is we are seeing a lot of investment coming into this space because of this interest. And as a result, there is a substantial amount of computing and big data that's coming in. GPU as a service is becoming more and more prevalent. And because a lot of GCCs are coming in, this is a combined confluence where the combination of GCCs and AI data centers is creating a very large opportunity for driving the India's data center market. There are 2 or 3 key things that we need to keep in mind from a data center boom perspective and what it means from cooling perspective, right? So the Indian data center obviously relies on intensive systems like rack units. There are linked to the heating, ventilation, and AC related to data centers, there are some targets that India has set in terms of cooling energy requirements, where we want to reduce by 25 to 40% by the 2037-2038 timeline. This is a national target we have. Okay. Why this is important is because we as a country are already looking at reducing cooling demand, reducing the refrigerant demand. And this aligns very well with the requirements of data centers in terms of how we need to work on reducing the impact that the data center cooling demand has on the overall economy. Now, there are key elements that we need to keep in mind for the refrigerate transition landscape. The first one is compliance with HFCs being phased out, along with global commitments. So we are trying to align with the Kigali Commitment and the Montreal Protocol to phase down high global warming potential hydrocarbons. In terms of the metrics, we are trying to, as I mentioned earlier, fulfill the refrigerant demand to reduce it by 25 to 30% in the next 10 to 12 years. Now, coming to India's digital infrastructure, there are 4 key things from an energy perspective that we need to keep in mind. The first is we have already surpassed a 1.5 gigawatt capacity of active operational stock, and we are adding 500,000 server racks equivalents, right? Which means that there is a substantial growth projection where we are looking at up to 3 gigawatt by 2028, which is going to consume upwards of around 3%. Right now, we as data centers in India consume around 0.8% of India's current electricity demand. This can go up to 3% by 2030. And the key focus areas where this is happening is Mumbai, where we have more than 800 megawatt, followed by rapid build-outs in Chennai, Hyderabad, and NCR. So when you're looking at data center cooling, if you are a company which is focusing on cooling technologies, you need to be looking at these hubs to create and serve that market. The global local impact. So as I mentioned, globally, data centers account for 1.5%, and in India, it is 0.8% of the electricity demand. And this is likely globally to go up to around 3.4% and 3% of the national grid. So what this means is that increasingly, data center energy consumption and cooling requirements are becoming a very large element of the overall data center market. Now, we need to understand, we have heard a lot of the earlier speakers talk about the loads and the potential opportunities. So what we will do is we will quickly go through the key elements and then talk about the emissions. So in a data center, you've got the infrastructural load and you've got the IT load. The critical core is the IT load, where you've got energy consumed exclusively by the computing hardware, okay, which includes the GPUs, the networking switches, the storage arrays, and so on. And then you've got the infrastructure load, which focuses on the electrical and mechanical infrastructure to support the IT load and other components. And these include the transformers, the UPSs, the lighting, the environmental control, and battery charging. The key thing to remember here is cooling mechanisms dominate the infrastructure load, accounting for around 30 to 40% of the entire facility's power allocation. Now, in that context, there are two key metrics that we need to keep in mind. Power usage effectiveness, which is a ratio of the total facility power, which is a combination of IT plus infrastructure, divided by the IT power. So this helps us understand how efficient the capacity of the data center is. From a water usage perspective, we track the liters of water used per kilowatt of IT consumption. And this is essential because this allows us to know what is the water consumption for this cooling load that is required. Now, what are the key differences, when we look at cooling from a thermal perspective? In traditional data centers, we are looking at around up to 10 kilowatt per rack. But here in AI data centers, which are growing in number, this can go tenfold. So this can go up to 100 plus kilowatt per rack. The cooling method that's typically used by traditional data centers include raised floor containment, whereas for AI data centers, we are looking at direct to chip and mandatory fluid loop. So liquid cooling is a key element of dense AI data centers. On the grid power sourcing, predominantly we are looking at grid plus power backup systems, but in a high density AI cluster, we are also continuously looking at green renewable energy, because the demands are so high that unless we are able to get renewable energy to the data centers, this is going to place an inordinate amount of stress on our existing grid infrastructure. This brings me to the carbon accounting piece. So in a data center context, the scope 1, and we are talking about the greenhouse gas protocol here, the scope 1 are the direct operational emissions, which are accounted for by the refrigerants. Essentially, these are the fugitive chemical greenhouse gas emissions, which are arising from, let's say, leaking chillers or anywhere in the HVAC maintenance cycle. The other element within scope 1 are the DG, the diesel generator sets. These are essentially used for power backup and used during grid failures. These are especially important for tier 4 data centers where they have very, very stringent SLAs. The second piece, or scope 2 emission, pertains to purchased electricity, where we are looking at currently state power grid supplying the baseline. But additionally, we are also looking at identifying power purchase agreements through localized off-site and on-site solar and wind vendors. As I mentioned earlier, this is very, very essential especially for load-heavy AI data centers, because the density of energy required is very high and can place a load on the grid. The third element, which is scope 3, is around the value chain and embodied carbon. Now, here we need to understand and move out of the critical area of the data center and look at the upstream life cycle emissions constructed with the building itself. So when we are creating these large data centers, we need to be looking at the floor slabs, the perimeter walls, the insulation, and see what is the embodied carbon in these elements. And when this is happening, we need to also look at what is the life cycle cost in terms of the upstream transportation emissions and the fuel related emissions for transporting these materials to the site when the construction is happening. Now, all of these can be evaluated using something called a life cycle assessment of the construction itself, which gives us an understanding of what is the embodied carbon. And then we can look at the scope 1 and 2 emissions to reduce the operational carbon emissions. So in summary, if we look at the different scopes, scope 1 predominantly is driven by generators and refrigerant leaks. Scope 2 is focused on the carbon grid and, in current situations, renewable energy. Scope 3, which accounts for anywhere between 30 to 50%, is based on the construction of that asset. So what we need to keep in mind is the energy from the grid intensity varies by up to 100 times. And therefore, it's very important to make sure that we are bringing clean energy into the system. From a scope 3 perspective, we need to understand what is the impact of the concrete, the steel, the chips, everything that's coming into the data center and is going to be stationary there, and how we can reduce the emissions there. From a water perspective, we need to look at 4 key elements. One major challenge is, see, traditional evaporative data centers use huge amounts of water, okay? And this is done to drive down the air cooling temperatures. And we can measure this using the water usage effectiveness measure, okay? What we need to understand is, particularly in an India context, a lot of these data centers are coming up in hubs which are already water stressed. And the combination of regulatory gridlock and localized friction leads to substantial resistance for establishing these data centers in these locations. So there is a lot of tension that's happening, and therefore increased reduction in water table locations at these sites can lead to severe challenges from both an economic and social perspective. The last is focused on the future, where we need to look at deploying advanced closed circuit systems and fluid containment strategies to minimize this evaporative loss. And interestingly, what is essential to understand is, when we introduce these closed cycle systems, in fact, when the data center energy usage requirement increase, they require lesser amount of water, contrary to popular behavior, because we are working with closed cycle systems. So when we are looking at these more energy intensive data centers, it's very important that we introduce these closed cycle systems to reduce the amount of water that's being used. So in summary, if I look at the water availability versus demand, the reality is 600 million people of the 1.4 billion are under high extreme water stress. And by 2030, India's water demand is due to double, which means that cooling water for these data centers currently compete with the same local water that people use in their cities, farms, and in industries. What is worsening the situation is the cooling demand itself is increasing. So 1.5 gigawatt is the installed capacity. And what this means is, by 2030, we will need 150 billion liters of water usage, which is actually 150 billion is the current usage, which will double by 2030 to around 300 billion liters, which is massive. Currently, a single 100 megawatt campus roughly needs 2 million liters of water per day. The reason this is so important to understand is because this is the same pool that all of us are drawing our needs from. So when we are designing data centers, when we are designing the servers, it's very important to be mindful of what are the technologies that we are bringing in to reduce the water consumption. And because 50% of India's data center are in water-stressed regions, okay, we've got 278 data centers nationwide, of which 75% sits in these 5 states of Maharashtra, Tamil Nadu, Karnataka, Telangana, and UP. And therefore, this is no more just a local or regional problem, it's a national problem. So what we need to remember is when we are siting data centers, we need to choose lower stress locations, even if it means a little higher cost, because it will ensure that in the long run, you have more sustainable operations, better availability of water, lesser disruption from local communities, less friction with the government, and so on. We need to ensure in those locations, we are recycling and reclaiming and reusing the water as much as possible, and finally shift to low water or closed loop systems. So these are some of the perspectives that I wanted to share with you all today to help you understand what are the key elements from an emissions perspective and from a water usage perspective that we need to keep in mind when it comes to addressing the cooling demand for data centers. Thank you, and happy to take any questions.
Yeah, thanks a lot, Indrajit. Also, sort of an eye opener for all of us as we are talking about data center growth becoming almost 5x, 6x times. What will be the impact on our water systems, water resources, and the unintended consequences if we don't design and plan for it from the beginning. So thank you so much. And with that, we have come to the end of all presentations. We have roughly 20 minutes for the Q&A, and I see already some questions that have been posted the comments section as well as in the chat window. We are going to maybe start with the questions where the participants have clearly identified the speakers that are in a sort of best position to answer those questions. So maybe we can start with you, Jabin, if you are there. There is a question for you, Jabin. Can you give me a nod if you are?
Yes, I'm here.
Yeah. So, Jabin, the question for you is, considering that the energy source is low grade, what percentage of energy conversion efficiency do you think would be realistically achievable? Based on your experience, what efficiency range should we expect under practical operating conditions?
So, as you know, this when I say 1 gigawatt of data center, we have around 1.25 gigawatt of heat. We think that we can get close to 35 to 40% efficiency from those from the waste heat, but the PUE can go from 1.25 to 1.05. We have done a lot of calculation and modeling to show this is possible just by using the waste heat.
Excellent.
It varies from of course, all these things varies from place to place because outside conditions, ambient conditions matter quite a bit, but this is what we have seen.
So thanks a lot, Jabin. A related question on the waste heat from Ayan Sangupta. Is there any way that the DC waste heat can be utilized for desalination applications, especially for the locations near coastal areas in India? You can also.
So what we are seeing is that this waste heat is better utilized for atmospheric water generation. That means you take the water from the air. There is a lot of water in the air, so you don't have to go and desalinate. It is much more efficient to absorb the water from the air and then use waste heat to regenerate that water. So there are many startups across the world and even in India that have started to produce these atmospheric water generators. These atmospheric water generators are producing one 40-foot container. At the present time, they are able to produce up to 1,000 liters per hour.
Excellent. Thanks, Jabin. So we have a question for you, Jennifer. And if you are available,
Yes.
yeah. So, and if you can,
Yeah, absolutely.
get the question and respond.
To take a look. So the question that was raised by Mahesh, thanks for raising this. So I think that both immersion cooling and free cooling in winter approaches, they both have potential. But again, their suitability depends on the climate, the workload, and customer requirements. The first one, immersion cooling, can be effective for very high density computing. But it's good to note that there are still considerations around equipment compatibility, maintenance, and operational readiness. So that's a big one. On the free cooling, I believe it can deliver strong efficiency benefits in cooler climates or during winter months. But the opportunity is more limited in hotter or more humid markets. And on the second point around operating at higher temperature, it can reduce cooling demand and may reduce the cooling capacity required, but this depends on whether the IT equipment is, again, designed and warranted to operate reliably at those temperatures. So from an operator perspective, we will assess the whole system, including equipment, their limits, the airflow, the resilience itself, and the customer requirements. Again, reliability remains the priority. So that's to answer Mahesh's question. And if I may, there's another question that I can answer straight, raised by Path. The question is around the fragmented reporting that remains a major challenge, and what else can we be doing? I think really here the priority is not necessarily to add more regulations, but really to create greater harmony, greater consistency in how requirements are defined and applied. The most important thing we need to start with is common definition, common system boundaries, and common calculation methodologies for key metrics like PUE, WE, so that performance can be genuinely comparable across operators and markets. The second point, regulation really should start with consistent disclosure and assurance before moving too quickly into like defining universal threshold, because again, climate, water availability, facility design, they differ significantly by location. And then for scope 3, I think we really need to start with clearer life cycle accounting standards, and that look into supplier data, product level information like EPDs, environmental product declarations. And ideally, these requirements should align across jurisdiction, not easy, and build on recognized international standards rather than creating so many different overlapping frameworks. And this is where industry bodies like APDCA that we mentioned earlier can really help bringing data center operators together and policymakers to kind of create those consistent practical approach that will work with those common definitions. Yeah, I hope I answer your question, Path. Thank you.
Thanks a lot, Jennifer. There are two questions that I see where Indrajit, it will be very useful if you can, reflect on those questions and, respond to them. One question is related to, are there benchmark standards or targets, global or Indian, that the data centers are expected to meet for cooling efficiency?
Okay. So I think from a standards perspective, India, unfortunately, not a lot. but we do have standards that we can look at from a global perspective. And that is where I mentioned about the, if we look at, let's say, the PUE or the WUE, okay, there are certain benchmarks that we use. From a global perspective, there are certain benchmarks. For example, if we look at a PUE, theoretical ideal is 1, okay, so there is no cooling or overhead losses. But in real life, the global PUE is around 1.54. Hyperscalers often are able to achieve 1.1 or 1.2, but usually in favorable climates, okay. So that is typically from a PUE perspective. Okay, from a water perspective, we can look at free cooling, we can look at economizer operation and reduce compression. So that's something that we can look at. Okay, in India, typically the PUE benchmarks are a little higher, around the 1.4 range. There are certain advanced designs with economizers where you can achieve a 1.3 benchmark. Okay, so BEE actually has certain guidelines that you may want to look at. And additionally, from a design perspective, you can look at ASHRAE, which is for HVAC design, TIA 942, which is for data center infrastructure, and of course, the National Building Standard. Okay, so that's on the standard piece, right? What was the second question?
So this was all. So the second question, Indrajit, from a participant, China is building underwater data centers to utilize seawater for cooling. What is the environmental impact of underwater data center other than the improved PUE?
That's an interesting question, Prosenjit. I don't think there is a lot of research out there on the impact of underwater data centers on seawater. Now, interestingly, it's not just China, but Microsoft has been doing this for a while now. Okay. Now, one thing from a pro perspective to keep in mind is these immersion actually reduces data center failure substantially. So there is obviously a very strong use case for going for such data centers. However, what we need to understand, based on some, if I look at just the fundamental first principles, what it will do is it will lead to a lot of localized heating of the water around, which in turn is going to have an impact on the microscopic flora and fauna in that area. Okay, I don't think we have studies which showcase what that warming effect does to local species in and around that region. So, to my understanding, I have not seen a lot of assessments, but definitely, while there is a use case for the business, we need to be mindful that in addition to the adverse effects of global warming on marine ecosystem, this is going to create further damage to that ecosystem, predominantly because we will be heating up local areas of water bodies substantially due to this high heat. I think there was one more question on the Kigali Amendment transition pathway. So while we probably need to expand this on a little bit more, but I'll try to give a brief answer. Okay, so there was a question on whether we can transition to, let's say, R513A or 1234. I don't know who's asked the question, but we would need to look at it on a case by case basis. Okay, for example, if today it is using R134A and we need to move to R513A, that is relatively easier because it is an engineered retrofit. Okay, and there are many OEM approved platforms which typically, with a combination of refrigerant replacement control plus software changes, we can achieve those rather than a completely new plant. However, if we were to move to R1234ZE, which is a much lower GWP, this may not be very easy because under the ASHRAE safety classification, okay, this R1234ZE, which is mildly inflammable, behaves differently from a R134A, which means that we may need to replace the entire chiller package, okay, or do a very deep OEM conversion. So when we look at these options, we would need to carefully consider each option and see what it means from an impact perspective. I hope that addresses those questions. Anything else that we have?
Thanks, Indrajit. No, so on the same question, Dr. Santosh, if you have anything to add.
I think Indrajit has answered, but yes, for a few HFC refrigerants, we have direct drop-in replacements of refrigerants, and a few HFOs can directly replace the component, like compressors mainly. Other components will be more or less same. A few thermophysical properties like volumetric displacement, etc., will change. So those are manageable as well with some drop-in replacements. Otherwise, because the Kigali Amendment. This phase down will start by 2032. So the facilities developed today or maybe in the next year will have sufficient time to move towards the alternatives. I think that answers the question.
Thanks. And I see like one question that maybe many participants have asked. It's related to how do the technologies like direct to chip liquid cooling compares with the traditional cooling when it comes to efficiency or PUE improvement. Maybe that's the question that also relates to why in case of hyperscalers, the share of cooling edge percentage of the total data center, energy consumption is lower. So maybe Santosh, you can.
Yes, so
answer
I
that.
can try to answer. In the hyperscalers, so there are two things basically. So one is that the IT demand, the IT energy demand is increasing, and we are shifting toward because once we have 30 kilowatt per rack, 40 kilowatt per rack, so we have no option then in the air cooling type, and we have to move toward the liquid cooling side. When we move towards liquid cooling side, the air actually being replaced by the liquid. Some fluids are there, maybe water or some other fluids, a mix of fluids, and that has higher heat carrying capacity as well as thermal conductivity. So, and the other thing is that we are taking the heat from the direct the source, from the chip level, from the component level, not in the like in the air cooling system. It happens that racks are generating heats, and heat is being picked from the room or the space surrounded by the servers. So, two, three things which leads to lower the energy demand by the cooling system is that that fluid we are changing, heat carrying capacity and conductivity is increasing of the fluid. We are taking the heat directly from the source so that efficiency losses in between are decreasing. And in the hyperscalers, actually the scale also plays a role in the co-locations and the enterprises. We have the smaller capacities. So when we move toward the gigawatt scale facilities, that scale thing also comes into the picture, and we have better operational and management of the system. So that enhances the efficiency of the cooling system.
Thanks. So basically, directly, first attacking the source and then using a better medium instead of cooling the air. So again, thanks. I don't know if there are any other questions in the chat box, but we are at the top of the hour. So in case there are more questions, we'll be sharing the email addresses of the speakers, the email addresses of the AEEE team. Ozone Cell team will also be available to all. I see Aditya Ji wants to come in. Aditya sir.
First of all, thanks for giving a very good presentation by all the speakers. I want to know that is there any guidelines available for design of building envelope and ventilation system for data center to reduce the basically cooling energy demand? I am laudable. Can you hear me?
Yes, sir, you are audible, and maybe Indrajit. Yes, sir. We
Yeah, I
could
think
hear
I
your
mentioned that.
question.
So what you can do is you can look at Bureau of Energy Efficiency. Okay, they have the best practice guidelines for data centers. Other than that, you can look at ASHRAE guidelines. Okay, for HVAC. You can look at TIA 942 for data center infrastructure. And of course, there are some elements of the NVC, which is now the NVCS, from a building code perspective. So I think we'll need to combine these 3 or 4 standards to put together what would be an optimal way to build data centers.
Okay, thank you. Another question is regarding end of life management of refrigerant. So is there any guidelines or best practices to be adopted for management of refrigerant after end of life equipment or something with respect to data center?
Santosh or Jubin, anyone from the speakers want to?
Zubin, would you like to answer that?
Ajbir.
So maybe I can try,
Yeah.
sir. So in the base like life cycle refrigerant management, so because data centers has very concentrated, very high amount of refrigerants in the chillers, and that has some commercial as well as the environmental interest. So like manage the commercial interest. So because we have the large amount of refrigerants stored in a single place, so we have because of the economic interest, they do collect it and because the data centers are very sort of luxurious facilities and they have all the remote and sensors and control systems. So when the leaks start, they have better management of the refrigerants and the leakage and emissions. Also, other professional trained technicians are there to service and maintain the facilities. So I think a bit comparatively, if we see in the data centers, better LRM implementation is there compared to other air conditioners or small facilities. I hope this answers your question.
I would just like to add, so, while there are no exact guidelines, but the ozone depleting substances rule 2000, that has regulations on the manufacture, use, import and export, and the safe handling and disposal of refrigerants. So that is one thing that you can look at. Of course, there are references made in e-waste management rules or hazardous waste rules. That's one part. But globally, if you look at Montreal Protocol has the information on phasing out of the ozone depleting substances and phase down of HFCs. So these are 2 key pieces that you may want to look at. From a EU perspective, which is actually one of the most stringent, the EU F-gas regulation 2024/573, that has mandatory recovery of refrigerants at end of life. So if you're looking for a specific framework, you may want to look at the EU F-gas regulation. I hope that helps.
Thanks. Thank you. So Aditya, sir, we have exceeded the time. So, and we have also noted the questions that other participants have asked. So with your permission, can we go to the last section of our workshop, which is the vote of thanks and the next steps?
Sure.
Okay.
Sure.
Okay. Thank you. Thank you so much, everyone. First of all, I thank the Ozone Cell MOEFCC for this opportunity given to IEEE to be a part of this study and conduct this workshop. My sincere thanks to all the speakers today for finding out time and sharing their experience, and also to all the participants for patiently listening to the workshop, and also once again apologies for the delayed start. What we'll do next, we are going to compile the key discussion points, which will email it to everyone along with the contact email of all speakers. As mentioned by IEEE team, we are going to seek consent from all speakers if their presentations can be circulated to all the participants. once that consent is received, we are going to also share the PPTs. Regarding the recording available on YouTube, again, we'll look at the privacy policy and also the consent of speakers, if they are okay for us to upload the recordings on YouTube, or at least share it with the participants. As I was mentioning earlier, as part of this study, we are also planning to do assessments of data centers. So in case if anyone is interested to make their facility available for study or be part of the primary research and consultation, please do register your interest. We are also trying to compile some case studies capturing good practices in design, or case studies focusing on operations. So in case you have developed any case studies, or if you wish to participate in those case studies, please share your interest with AEEE team. So yeah, over the next couple of months, we'll be engaging a lot with the stakeholders, trying to collect information and trying to collate all of that. And maybe after a gap of 2 months, sometimes in the month of August, we'll have the second workshop in this series, where we are going to then talk about and share what's the actual information coming from the ground, and what kind of directions and pathways the policymakers can take in India and the participants can take in India to enhance the sustainability in data centers, both from efficiency, water usage, and other environmental friendly initiatives such as use of better refrigerants. So with that, we come to the closeout for today's workshop. Once again, thank you everyone, and have a nice day. Bye bye.
Thank you very much.